All right, how's it going, everybody? I am here on Friday, April 9th. Today we're going to be talking about sections 10.3 and 10.4 today. We're going to be able to knock these ones out a little bit quicker than we did 10.1 and 10.2, partially because you are already pretty comfortable with polar coordinates as opposed to parametric equations. I think we're something that we really need to spend a day on first here. So this week we're going to hit 10.3 and 10.4 kind of as one topic right here. It's going to be pretty I don't want to say it's easy. It's going to lead us to some integrals that can be certainly difficult, but conceptually speaking, the formulas that are associated with this stuff, I think you guys are going to be on board pretty quickly. I think it's going to be very reasonable for us to cover 10.3, 10.4 today in one little video here. Um, our other video this week, or I should say videos this week, are going to be associated with section 11.1. And the weird thing that's happening this week is we are in fact covering three sections. We are in fact actually going to have three videos this week. However, there's going to be one video for 10.3 and 10.4 today, and then there's going to be two videos that are tied to section 11.1 because there's sort of like a I don't want to call it a bonus topic because that makes it sound like it's extra and optional. There's one side topic that the book assumes that you're familiar with, and I know that most of you are not, that I kind of need to kind of go back and cover as well. So that'll get its own separate video. So I do just want to kind of point out to you guys, Chapter 11 is I don't want to be scary, but it's sort of a monster. It's a very, very, very big idea. It covers there's 12 sections in chapter 11 that we're going to try to get through before the semester is over here. We are going to be probably covering more like 3 sections per week instead of 2 sections per week coming up right here. And this is going to deal with a lot of concepts that you guys are not previously familiar with. It's going to deal with writing proofs rather than doing computations. Chapter 11 is its own whole different animal out there that's pretty wildly different from the rest of what we've been doing this semester. Despite that, it's still very much a core essential concept associated with calculus and calculus related ideas. So it's not like we're not doing calculus anymore, but you're going to see chapter 11 is going to be a pretty big departure from what we've been doing otherwise this semester here. And we're getting that started this week. So 11.1 is our other topic of the week, other than kind of wrapping up our calculus and other settings topics, which is chapter 10 here. So two things to say before we get started. One, last week we covered parametric curves, then calculus with parametric curves. And we did that in two different sections because you weren't all already familiar with parametric curves. This week, we're talking about polar curves and calculus with polar curves, but you guys are already familiar with polar and you are manageable in polar land as opposed to parametric land. So what we're not doing is we're not going to spend a day reorienting yourself with polar coordinates. You should just know that from trigonometry already. I am going to give you the refresher, but more of like the 20-minute refresher instead of cover a whole section refresher. And then we can just jump straight into the calculus, which is why we're doing both videos, both sections in one day or one video here. The other thing that's going to be nice is that this calculus content that we're going to see today is going to very closely kind of mimic the types of things that we did with our parametric stuff. At the end of the day, our polar curves are just parameterizations in terms of theta. So we're going to get to use our same parametric setups as we did last week with our stuff today. So you won't see that this won't be anything too mind-blowing. We're going to get some equations that are not necessarily what you would have like blindly expected to see, but I think our process through all this today, you're going to say, oh yeah, we're using that. Okay, that makes sense. So the other thing I'll say here is that you're going to see a lot more polar content with calculus when you guys take calculus 3, Math50C. And so we're only going to touch on it lightly today because polar becomes a much more practical setting to be in calculus environments once we're doing multiple integration, once we're thinking about things in 3D. So there's lots of three-dimensional shapes that are much better handled in polar than they are in rectangular coordinates. And so trust that once you go to take 50C, you're going to get a lot more experience dealing with polar related ideas in calculus. Today we're going to touch on a little bit here, see that we can handle some ideas of derivatives, integrals. We're going to do kind of our spread of things. We're going to look at derivatives and tangent lines. We're going to look at areas, and we're going to look at arc length, all in polar here today. And they're not going to blow your minds too much conceptually. Like I said, they have potential to lead us to some relatively gnarly integrals that we may or may not be able to do, but at least conceptually, at least constructing the integral is something that you'll be able to do here without too much difficulty here. So let's go ahead and get on into it here. So the basics of polar coordinates, what you learned in trig. You all know how to convert between polar and rectangular coordinates, r and theta versus x and y. If not, then you should go to a tattoo parlor and you should tattoo this maybe on your forehead. If not, then at least on your forearms that you can look at it every day for the rest of your life. Our polar equations, when people come to me, and especially when I get my Calc 1, Calc 2 students are like, oh, I forgot my polar coordinates. I give them the meanest look, and I like to think of myself as a pretty nice and pretty approachable guy until people tell me that they've forgotten how to convert. And the reason why I get upset about it is because you don't need to remember the formulas, you only need to remember the diagram, and the diagram is easy because it's just the most generic right triangle that you could ever draw. This is all I remember when I do my polar coordinate stuff. I then build the equations myself based on what I see here. Um, so some things that I can see are, if my goal is to find out what is r and what is theta given x and y, then I know that if I want to figure out what's theta given x and y, that there's clearly a tangent relationship because y is opposite and x is adjacent. So I'm making the statement of tangent of theta equals y over x. I can see that I can solve for theta by taking an inverse tangent. Similarly, if I knew x and y, just like in this case right here, and I wanted to solve for r, we can clearly see a Pythagorean theorem relationship right here. And so r is the square root of x squared plus y squared. So these are the two formulas where if you know x and y, you can solve for r and theta. So that's one set of relationships right there. Going the opposite direction, if I know r and theta, how do I solve for x and y? Well, if I know r and theta, I can see relative to the angle theta, r is the hypotenuse, x is adjacent, y is opposite. So therefore, opposite over hypotenuse should be cosine, should help us find x. Opposite over hypotenuse, that sine should help us solve for y. So I'm going to say here that cosine of theta is adjacent over hypotenuse, that's x over r, and we multiply r to the other side to get that x equals r cos theta. And almost identically here, sine theta equals y over r. We multiply r to the other side, y equals r sine theta. So there's our four trig equations that help us relate our x and y stuff to our r and theta stuff. You should never forget this because all you need is the diagram. The diagram gets you 100% of that information. If you ever forget these formulas, it doesn't matter. You just draw your right triangle again and just come up with them again. You can do the trig. It's pretty easy right there. So this is where in trig class I would now do some examples of converting points between rectangular and polar, and I'm just not going to do that because I know that you guys have done that. We can also use these to convert between polar and rectangular equations, not just locations. So here's an example we should do right here. What I would like us to do right now, and you should pause the video and do this yourself, is graph this equation. The reason that you should know how to graph this equation is because you can convert this to rectangular coordinates, and you can then and you should recognize the general form of the graph that we're seeing here. So I would suggest that you pause your video for a moment and see if you can convert this to rectangular coordinates and then determine what the graph should end up looking like. Great, so now that you've unpaused your video, let's go ahead and do this thing here. So r equals 4 sine theta. So here's the thing I'm thinking. If I need to convert this thing into rectangular coordinates, what I'm thinking is I would like to see some of these expressions pop up here. I'm not thinking that I'm going to see any tangent or tangent inverse or ratios of y's over x's cropping up right here being useful to me. So I don't think this is what I'm looking for, but I'm kind of looking for some of these expressions that are out here. So I'm kind of hoping to see things like, I hope to not see square roots in here, otherwise this is not going to be something easy for me to graph, but maybe seeing something in r squared could get me some x squared and some y squared. I see that I have a sine theta, and I know that sine theta needs to have an r with it for me to convert into y. So I almost have what I need on the right. If I feel like if I had an additional r term on the right, then I could write that as y. And similarly, I feel like if I had an extra r term on the left, then I could write that as an x squared plus y squared. So my sort of suggested maneuver right here is to say, if I multiply both sides of this equation by r, I think I'm in a better shape to convert this thing into rectangular. So I'm going to go ahead and multiply by r on both sides. And now that I've done that, r squared is going to be x squared plus y squared. R sine theta is going to be just y. And now the still non-ob, so this is just the convert to rectangular out of polar. We've done that. So we've kind of done step one of the instructions here. We converted to rectangular. Now what I want to know is, how do I know what this graph looks like? Well, what I'm seeing here is I know that x squared plus y squared equals a constant squared. That's just the formula for a circle right there, is basically what we stated. It's essentially the distance formula, because the definition of a circle is it's all points that are a constant distance from the origin. So I feel like what I want is to have x squared plus x stuff squared plus y stuff squared equals a constant squared. So the way I verbalize that, I'm kind of suggesting to you that I want to group up all my y information together and write one collective squared statement. So it's pretty typical that we go to complete the square when we're dealing with these circle-related equations right here, or maybe like ellipses or other things dealing with conic sections here. So what I'm going to do is I'm going to move all of my y stuff to one side. And now what I'd like to do is complete the square on just the y terms. So what I'll do here in this case is it looks like, what do I need to do to complete the square? You should be able to answer this. I want to add 4, I think, to both sides right here so that now these terms right here become x squared plus y minus 2 squared equals 4. Now this guy right here is the equation of a circle. With a radius of 2. And it's been shifted up 2 units. And we can see this because of this y minus 2. This adjustment is inside the parentheses, so it's sort of got that opposite nature of the impact right there. That before, in my general equation for a circle, I'd plug in 0 for y to get 0 for the overall y component. I now need to plug in 2 for y to get 0 overall for the y components. That's shifted us up 2 units right there. So this should be a graph of a circle of radius 2 shifted up 2 units. So that's like at a height of 2 right there. Therefore, that should be at like a height of 4, I think, right there. So in this case here, it is a circle, so the equation is written most simply in polar coordinates because polar coordinates are in general best for circles. Since it wasn't centered at the origin, the equation was slightly complicated here. Instead of just being r equals 2, that would be the equation of a radius of circle 2. It was r equals 4 sine theta because of that shift component that was going on right there. I still think this equation is simpler than our algebra equation down here. It's tough to convince people that this is going to give us a circle. I think that polar coordinates, it's more believable that those lend us towards circles a little bit better out there. I do think it's worth going ahead and taking a look at Desmos and seeing what Desmos has to say about this. Desmos, fortunately for us, handles polar coordinates just fine. R equals 4 sine theta. And we can see it does in fact give us a circle of radius 2 centered at a location that's been shifted up 2 units. And we can also verify this does agree with the algebra that we just did. And there we go. We can see that these are overlapping one another right here. They're clearly the exact same graph. Turn it on, turn it off, and we can see that's the same exact graph right there. So Desmos agrees that these two equations are equivalent to one another. One is in polar, one is in Cartesian, both representing the exact same object in space. So what else do we got here? So these are some things that we can do. We want to remember that when we're graphing polar equations, if your job is to graph an equation, it's often helpful to look for symmetries. And this last one, the algebra got me there because I just got out of polar. But if you're trying to produce a graph that is just remaining in polar form, you should remember that there are 3 general symmetries that we can in general go hunt for. That will help us, and again, as we've learned this semester, symmetry is your friend. Every time you find a symmetry, you're dividing your work into half, into quarters, something like that. It's always useful for us to find these symmetries. So one symmetry we can see is if we can swap all of our theta terms to be negative theta terms, then this should help us determine, do we have symmetry? Well, what symmetry would this be? I think in my diagram right here, if I instead looked at an angle that opened up with a if I look at a point in space through that I've rotated through an angle of theta to arrive at, what happens if I instead rotate negative theta as my angle? Well, what we can see is that these 2 points are a reflection of one another over the x-axis. So here we get symmetry over the x-axis. So this says if you can replace theta with negative theta in your equation and the equation remains identical once you sort of simplify it, then that says our graph is going to have symmetry over the x-axis. Another symmetry that we have available to us is the symmetry of saying, hey, what happens if you swap out all of your thetas for pi minus theta? And so a similar diagram here is going to say we maybe opened up theta for our original angle. Well, what if instead I do pi minus theta? Well, where even is that? Well, to do pi minus theta, I want to start at the location of pi, which is over on the left-hand side over here, and I want to subtract off the amount of angle that's associated with theta, which is this little guy over here. So pi minus theta is going to be this guy that's over here. All right. So if you can take your polar equation and swap out theta for pi minus theta and simplify your expression, and it's all equal to the original equation once again, then that's going to guarantee it looks like that you have symmetry over the y-axis right here. Finally, converting your r term to a negative r term right here. Now that's in a sense a little bit weird because we think of a radius as like a distance that's always positive. It does almost unfortunately make sense for us to talk about having negative radii when we do polar form stuff out there. In general, I think best practice is to not use a negative radius in most cases, but if you solve for one and get one, you should be able to manage that, you know. And so I'm thinking if we have some polar point that has some radius and some theta right here, I'll just call that r theta, then it should be the case that we can find a symmetric point over here that's located at negative r theta. And the thing that I like to think is if you have a fixed theta, like theta equals 6, then that should just be some like, okay, so theta equals 6 radians would be like this because it would be almost 2 pi radians. But what you should think of is that that line technically maybe extends both directions through the origin here. And so positive angles might go in our typical positive direction. But you should think if you decrease your value of r, and if this is the origin right here, you should just continue to decrease it in the negative direction. It should follow that same trend right there. So this is the same angle of theta in my diagram right here, where theta with the positive radius down through a radius of 0, and then continuing through to your negative radii in that same direction right there. So there's our negative r of theta right there. So this is sort of our like odd symmetry. This is like a rotational symmetry, like 180 degrees or pi radians rotation. So this is not a mirror image symmetry. This is a rotation-based symmetry. If it's okay for you to replace r with negative r, and when you simplify, your equation is exactly the same as it was when you started. For example, if the only r that shows up is actually r squared in your equation, then you should be able to replace r with negative r, and when you simplify, nothing actually is different from your original equation. Then that graph will have rotational symmetry where you can rotate the graph by 180 degrees, and it will land back on itself again. So these are 3 types of symmetries that are generally useful if you're looking to graph any kind of polar stuff by hand. Often the first move is typically ask yourself, do I have any of the 3 families of symmetries here? That would make my work a lot easier. Right? So just something to kind of be aware of. Symmetry is really nice for us in polar graphing. Let's go ahead and take a look at some shapes that I know that all of you guys have probably seen once or twice in your investigation of polar looking curves out here. I'm just going to go pop over to Desmos and take a look at each of these guys right here, so we can remind ourselves of some of the shapes that we expect to see. Then we'll go ahead and do calculus with some of these shapes. So these are typically like the 4 families of trig shapes or of polar shapes that we look at when we teach trig classes here. But man, it's often like a lot of work to end up graphing these. And this is on the long list of times we should say to yourself, stop and take a moment and say it out loud. Man, I'm glad I'm taking this class in 2021 when we have Desmos. And just picture taking this class in 1970 and being expected to be able to come up with all these shapes on your own and then say, man, this is really nice. That's where you should be right now. So let's go ahead and look at a couple of these guys right here. So in fact, I'm just going to type in a bunch of these right here. Slider for me. Oh, all right, I'll leave that right there for now. And then Okay, so I'm going to turn these off, and basically you guys are going to look over, and you're just gonna, I just typed a bunch of equations into Desmos here, and one of them didn't work, and I want to show you why. So basically these four general, okay, here's a pair, obviously sine and cosine, whatever, obviously sine and cosine, kind of whatever. So I just typed in of the four, one representative from each family right here. Let's go ahead and take a look at them here. So the first graph right here, this is the cardioid general equation. Obviously, you can have sine or cosine within this equation right here. We can have a plus or a minus within this equation right here. And what we can see is if we slide this slider of A around, it's basically just growing the radius of our thing right here. Obviously, it's not a circle, so maybe radius isn't a great word, but it's sort of got this sizeness to it, this amplitude, and we can control this with the a term that's right here. So when notice here that the coefficient of 1 matches the coefficient in front of sine because a is multiplying the whole thing, that guarantees that this is going to go through the origin here. Now instead, if we make it so that the coefficient on each of the constant term and the trig term are potentially different, then we can have ones that either don't go through the origin, like this guy right here. So this is a limicon. I'm sure I'm saying that wrong. It's supposed to be French for snail. And I think the snailness comes from this inner loop thing. So one of the things that we can see here with limicons is that if our A term is larger than the B term, then we don't go through the origin and we don't have a loop. If the A term and B term are equal to one another, then we perfectly come up and touch the origin. If the A term is less than the B term, then we develop this inner loop within the function, which is kind of really weird in the fact that we get this sort of parametric type behavior where we're at the same location in space, but there's actually two different thetas that brought us there. And you should notice that I don't care what theta you're looking at. If your radius is 0, then you could have a radius 0 with an angle of 20 degrees, a radius of 0 with 80 degrees, a radius of 0 with 1,000 degrees. All those are going to be the same place, right at the origin right there. So a little bit more interesting with these limicons here, and we can classify them according to A being less than B, A being equal to B, A being greater than B are sort of the three different cases that we see here for the limicons. And I think that these are also, and notice by the way here, as B gets closer and closer to 0, unsurprisingly, this just becomes the equation r equals a, which is just straight up a circle right here. So a limicon is sort of like a shifted and squashed circle a little bit right here. And it's really nice to be able to play around with these slider bars. Again, go ahead and say it to yourself right now. Man, I'm glad I'm taking this class in 2021. How nice. Very nice is the answer. We can squeeze them the other way also right there. So my next one is yelling at me. Notice I've got a little warning message right here. I'm trying to go ahead and graph the lemniscate. A lemniscate, Greek for ribbon. I'm just trying to graph that equation that's sitting right there. And Desmos isn't happy about this. Let's see what the warning message says. It says, you've defined R in more than... Wait, what? Oh, get out of town. That's not your issue with this thing. Fine, I'll delete all those things. That's not its problem here. Oh, try defining n. Okay, that's still not its problem here. There we go. There's the error message I was looking for. Polar equations must be linear in R. It turns out that Desmos is not down with you using R squared in polar equations. So I can fix that because I can just go ahead and do my... Oh, get out of here. Square root. Okay, I'll type it out again, I guess. Thanks, Desmos, for almost being the nicest thing ever, except for you're not. And then I'll delete all these terms right here. And it certainly could be the case that we would get the negatives of these as well. So I'm thinking that this should be R equals plus or minus on this thing right here. So I am thinking that these should be sort of like buddied graphs right there. And what we can see, again, is that we've got this parameter of A that's controlling some stuff, which seems to be like sizing. And we've got this parameter, some crazy look. Oh, but then a simple graph. Now, why is this graph all simple? And we just saw some crazy stuff. Well, what value of n do we have? I have a whole number valued of n. It seems like we're getting some pretty wild transitionary things when our n values are in between integers. But you should notice that this is sort of, and what I'm going to do right here is I'm going to make this 0.01 for my step. And let's just go from like 0 to 4. Will it let me do this right here? Yes, okay. So notice as we get really close to a whole number, it's sort of like these are like collapsing onto one another. Boom, to give us those two perfect loops when n is equal to 2. And then they sort of explode out there again. And they're all sort of rotating, 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 getting curving through all these cool looking shapes right here. But as this n value gets closer and closer to 3, we're going to see a bunch of these shapes are going to all fall in line together, and they're going to sort of collapse on one another to give us, it looks like now. So now notice a weird thing here with this lemniscate is that when we have n being an odd integer, there's actually twice as many loops. There's 6 loops, whereas when n was an even integer, we just saw that's exactly how many loops there actually were, right? And now I can let this go a little bit further out here to being like out to 10 or something like that. And so again, I'm going to be able to see that when we get to 4, I expect 4 loops. There we go. When I go to 5, I'm expecting twice 5 loops. So 10 loops at 5. Boom. We got 10 loops at 5 right there. Stuff like that. 6 loops at 6. But 14 loops at 7. And again, imagine discovering all this stuff without technology. Just imagine that and then say, dang, I'm glad I don't have to do that. So we can see some lemniscates out here, also some relatively common shapes to kind of arrive at in polar coordinates right here. The last one is one that's a little bit different from the rest, but one that I think is super, super relevant considering I'm also teaching my differential equations class this semester, and these shapes have been coming up quite a bit this week. Here's AE to the B theta is our spiral type shape right here. So I've got my sliders here. So what does it look like A is controlling? It looks like as I make A get bigger, it's just moving our starting location out. Notice our starting graphical location is like at 3, and here we are at 3 for A, 2.9, whatever. So it seems like A is just controlling sort of where we start, and that makes sense because you know that A represents the initial condition in that exponential function. B represents our growth or decay constant. Notice that B is currently positive, so it seems like we're doing some outward spiraling. But if I go ahead and make B, if I make B 0, then unsurprisingly we're a circle again. Notice if B is 0, this equation is just R equals A. So it's a circle of radius A, and we've got A being 3. But now if I make B negative, I went too negative too quickly there. Wait a minute, how is this? Why is, okay, I think if I make my A smaller, this will be nicer. So what if I make my A? Okay, come on, Desmos, you're just screwing with me now. All right, and I want to zoom in a little bit right here. So what's tough to see is that this thing is in fact spiraling in towards 0 right here. Why is it giving me such crazy... There we go. Maybe give it a less extreme decay constant right there. So this is going to have us starting at our starting location of 1, and I'm very gently decaying e to the negative 0.001 theta right there. And what you can see is that the spiral is decaying inwards now. In this case right here, it looks like the spiral just sort of like stopped right there. That's only because Desmos stopped progressing through more and more and more theta right there. The more I'm just sticking on zeros here, so now we're through 10,000 degrees or radians or whatever, and I can just keep going. So this circle, this spiral should be, no, don't throw up, should just be spiraling in forever right here. But technically in Desmos, if I go in far enough, I'll see the place where it stopped doing it because it's graphing this thing parametrically in terms of theta right here. But we could keep on going, and so the spiral should go forever. So this is notice this is like a question we asked last week. I think we parametrically defined a spiral, and we said how long is it? Well, it looks like we could have instead defined it in polar terms and also found the arc length in polar instead right here. So here's another way that we can describe polar curves right here. And you should notice that what is a spiral? A spiral is just a circle where the radius is actually changing over time. And here we've got that our radius is either decaying when b is negative 0.001, or maybe I can make it a positive 0.001, and you can see that this is starting at 1 and spiraling outwards now forever. And notice that this graph is really like choppy. If you can kind of see this, it feels like it seems like it's a bunch of like straight lines pieced together right here. Take differential equations next year and we'll learn why that's happening right there. What kind of numerical methods is this using to produce this curve right here? So there we go. Those are some shapes that you guys should vaguely recognize from trig right there. So when you go to see these in your homework, you shouldn't be too terribly surprised at these shapes that you're seeing right there. There's your little refresher. So there we go. Now let's go ahead and actually do some calculus with these polar curves out here rather than just kind of look at pretty shapes in Desmos. So let's go ahead and do our typical first thing is if we're going to do some calculus things, we want to be able to look at derivatives. So if we want to find the slope of a curve that's in polar form, we can use the very same ideas that we used from our parametric unit. If we consider our polar curves to be of the form r equals f of theta, so if they're always in r equals format, then we recognize that x and y are both equations that are parameterized by theta, because x is the same thing as r cosine theta, but we're thinking of r as being a function of theta. Well, it looks like x is parameterized by theta then. Theta is the only parameter that I need to know x. And very, very similarly, theta is the only parameter that I need to know y. So our goal is for ourselves to be able to find dy dx. That's what we want, is the slope of the curve. But what we need to do is exactly what we did last week and do a dy d theta divided by dx d theta. And this is pretty easy to do. So all I'm going to do is take the derivative of the y expression with respect to theta. I'm remembering that this is f of theta, but it's really just r, but that's to say r isn't a constant necessarily. R is a whole function of theta, so I can take the derivative of r with respect to theta. It's dr d theta, right? Because r equals is going to be like our equation, right? R equals is typically how we write lots of, not all, but lots of our polar equations that are out there. So when I do dy d theta, I'm taking the derivative of r times sine of theta. But r is really a whole function of theta, so notice I got to use the product rule right here, because this is a product of two numbers where both of them are dependent on that variable theta. So to do this product rule here, I'm going to first take the derivative of r with respect to theta. So this should be dr d theta. That's my first term. Times, I'm going to leave my second term alone. That's sine of theta. Plus, I'm going to leave the r term alone. And I'm going to take the derivative of sine and get cosine of theta. This is all divided by very, very similar expression for x. For x over here, I'm going to take it's the derivative of r cosine theta with respect to theta, acknowledging that r is actually a whole function of theta, so I got to use the product rule. So I'm going to again get dr d theta times, I'm going to leave the cosine term alone, plus this one I'm going to leave the r term alone, and I'm going to take the derivative of cosine, which is going to give me negative sine of theta. So it looks like this is telling me then that we should be getting that dy dx is going to be dr d theta sine theta plus r cos theta divided by dr d theta cos theta minus r sine theta. So now we have a not super awesome looking formula, but a formula that's easy to come by because it just required our two conversion equations for x and y out of r and theta, and a little product rule right there. I mean, that wasn't that hard to come up with right there. It looks, I wish it was a little bit cleaner and nicer than it is, but that's okay. This isn't going to be too bad to deal with overall right there. So let's go ahead and do an example with this guy right here. We now know how to take the derivative of a polar defined curve to find the y over x ratio of the slope of the curve, but given that the curve is defined in polar coordinates. So here's what I want to do. What I would like to know is on this polar curve right here, one of the things that I notice when we look over here in Desmos at all these curves is that there's a lot of things that are wrong with this thing right here in that this thing is failing the crap out of the vertical line test. Most polar curves do. It's got lots of places where we don't just have horizontal tangent lines, which is okay, but vertical tangent lines. And what is that? That's kind of weird to me right here. So one of the things that I might be interested in asking is, given this curve right here, r equals 1 plus sine theta, my question is, where does it have vertical tangent lines? Where are the vertical tangent lines, and how might we go about finding those? Well, what would you say the slope of the curve is if the tangent line is vertical? And this is one of those things where I want to say some technically bad math statement here. So it seems like I want to find where dy dx is undefined or is equal to plus or minus infinity, right? Now, obviously, infinity is not a number, so we never find the slope is equal to infinity. But if we can see where our slopes are getting infinitely steep as we get closer and closer to that point, those are going to be the places that have that tangent line that looks like that. So how am I going to find those? I don't know. Let's set up our derivative statement and see if we can get at it right here. So I'm finding dy dx is going to be equal to, and we've got our formula that we just stated right here. So using my formula up at the top, what do we got? Well, first things first, take the derivative of r with respect to theta. Okay, all right, all right. I'll actually just write out the formula here. dr d theta sine theta plus r cos theta, all divided by dr d theta cos theta minus r sine theta. So let's go ahead and do it here. So dr d theta, derivative of r with respect to theta. Well, derivative of 1 goes to 0, derivative of sine goes to cosine. So I'm going to get cosine theta times sine theta plus the entire equation r, which is 1 plus sine theta. That's what r is, times cosine theta. All divided by, and now we do it again. The derivative of r is going to be that cos theta times cos theta minus the entire r equation, 1 plus sine theta times sine theta. Now, you know that what we're looking for is we're looking to see where is the derivative undefined. How could it possibly be that the derivative is undefined? Well, it seems to me like the way the derivative is going to be undefined is if the denominator of the fraction that represents the derivative is equal to 0. So I don't even think I care about the numerator of this fraction anymore. I think I really just care about finding where is the denominator equal to 0. So I'm just going to simplify only the denominator here since I think that's all I care about. It looks like this should be minus sine theta minus sine squared theta. All right, all right. So I want to know where is the derivative denominator equal to 0. Where the denominator of the derivative is equal to 0. So what I want to do is I want to solve the equation cosine squared of theta minus sine of theta minus sine squared of theta is equal to 0. So can we solve this? The answer is yes, we can. So what I'm thinking to myself is this. It seems like we've got sines and cosines, but we have a minus between them, which is a huge bummer. If this was cosine, if that was just a positive sine squared on the end, this would be a piece of cake because cosine squared plus sine squared would be equal to 1. We'd be getting sine theta equals 1. We'd be home in a heartbeat right there. We'd just get pi halves plus 2 pi k. We're done. We don't have that. So it looks like we're stuck with a little bit of squared trig terms, which means to me I'm thinking about our quadratic informed trigonometric equations here. The thing that I'm seeing is that which one do we want to pick, sines or cosines? Well, I've got a standalone sine here that seems like it's going to survive either way. So that tells me let's convert our cosine information into sine information so that we can write a quadratic sine function right here. So I'm thinking I'm going to write this as 1 minus sine squared of theta minus sine theta minus sine squared of theta equals 0. I do a little bit of simplifying. Negative 2 sine squared of theta minus sine theta plus 1 equals 0. I hate having a negative on my leading coefficient right there, so I'm just going to run a negative through this guy. And now what it seems like is I could make a little bit of a variable substitution here and be in a place where I can make this happen, right? So let's let A be sine theta for the moment here. And let's take these two statements here and see if we can solve for the locations of interest. So 2a squared plus a minus 1 equals 0. I'm going to go to the quadratic formula and see negative 1 plus or minus square root of b squared minus 4 times a times c all over 2a. That's going to give me a being negative 1 plus or minus, what do we get? 1 plus 8 square root of 9 over 4. Looks like a is going to be negative 1 plus or minus 3 over 4. And then I can do my plus route and my minus route for the quadratic formula. There's my plus route, there's my minus route. If I do a plus in here, negative 1 plus 3 is 2. 2 over 4, a is a half. Alternatively, if I do the minus route, negative 1 minus 3 is negative 4. Negative 4 over 4 is going to be a negative 1. So it seems like I've found the two values of a that make this true. But a was really sine of theta. So let's go ahead and get our sine of theta stuff in here. So a equals a half. This is the same thing as me saying that sine of theta is equal to 1/2. Where does this occur on the unit circle? Well, I'm picturing on my unit circle here, we want to get to a height of 1/2. So So I'm picturing this guy and this guy being my two answers. This looks like our lower of our two standard angles right there. So I'm thinking this is like 30 degrees or pi sixths, and then 5 pi sixths over there. The other thing that we're interested in here is where is a equal to -1? That's the same thing as saying sine of theta equals -1. And where is this going to be on the unit circle? This one's our slightly easier one right here. Our height is equal to -1, so that's just where we hit the bottom of the unit circle. This is going to be theta is at 3 pi halves right there is where we get down to that -1. So let's stop and take a moment and see what we did right here. So our goal is to identify the x, y coordinate locations where this polar curve has vertical tangent lines. We found the derivative of the curve so that we can identify all of its slopes. We took the denominator of that fraction that was representative of the derivative and set it equal to 0, because what I want to know is where is dy dx undefined? Where are we dividing by 0 when we compute dy dx? That's where I'm thinking we're going to get those vertical tangent lines, infinitely steep tangent lines. So this was our denominator. I set it equal to 0. I solved the trig quadratic equation right here, and I found that these are the three angles that will result in us dividing by 0 in our derivative expression. So I'm thinking that these are the three angles at which we're going to achieve our vertical tangent lines. But these are in terms of theta. I want them in terms of x and y. So what are we going to do right now? Right now, all we know is theta. I can't convert to x and y if I don't also have r. So my first thought now is it seems like I need to first convert my theta information into r information. Then once I know both theta and r, I can convert those into x and y using our basic equations out there. Fortunately, I have an equation up here that relates theta to r, so I think I can plug in my three thetas to get out my three r's, then use my three r theta pairs to compute my three xy pairs, and then we can see where they're going to live on a graph. So this basically just sounds like a bunch of like conversion information right here. So I'm thinking that with the equation r equals 1 plus sine theta, that's our equation right there. I currently know my theta values. I want to convert them into r values and then into xy values. So our r values, so what I'm going to do is I'm just going to make a table. I think it'll be easiest here. So our r values from above were pi sixths, 5 pi sixths, and 3 pi halves. Those are our three values of interest here. Oops, and I wrote r, which is crazy because those are all theta. Now I want to go ahead and compute what is r from theta. So that's going to be r equals 1 plus sine of pi sixths. I know that sine of pi sixths, well, in fact, I've got it right here. What is the sine of pi sixths? It's 1/2. That's literally what we were saying in this equation right there, right? So that's going to be 1/2. So that's going to give me in total 3 halves for that r. This is 1 plus sine of 5 pi 6. The entire reason we got pi 6 and 5 pi 6 is because those two have the same sine value. So sine of 5 pi 6 is also a height of 1/2 right there. So we're going to get 3 halves again. And then down here for 3 pi halves, falling slightly off the bottom of the screen here, we're getting 1 plus sine of 3 pi halves. And sine of 3 pi halves is -1 because we're all the way down at the bottom. And so this should be giving me a radius of 0 associated with that point right there. So the point is, I now know my r comma theta ordered pair for each of the three locations of interest. I just want to convert those into xy locations because that's just what the problem asked me for here, right? So let's go ahead and convert into x right here. We know that x equals r cos theta. And so I'm going to do my r cos theta. 3 halves is my r. Cosine of pi sixths, and that's going to be for me 3 halves times the cosine of pi 6. If sine of pi 6 is 1/2, then cosine of pi 6 has to be root 3 over 2. So I think that I'm going to be getting here 3 root 3 over 4. That's 3 over 2 times root 3 over 3. I want to similarly do here, radius of the second point is also 3 halves times the cosine of the angle for the second point, which is 5 pi sixths. Now I'm recognizing here that 5 pi 6 should have a matching term as the pi 6 did, but the cosine is measuring left-right. So I'm actually going to get a negative of that same number for cosine right here. So cosine 5 pi 6 should be negative root 3 over 2, and therefore I'm going to get a negative 3 root 3 over 4 when I do that multiplication. Finally, my x-coordinate for this last one down here is going to be r times cosine of theta. Obviously, this is just 0 times -1, so I'm going to get a 0 for my x-coordinate there. And so now I've got all three of my x-coordinates, and finally we want to go ahead and check out our y-coordinates over here. And then once we're done, we'll just state our answers as xy pairs here. So we get our just kind of grouping it all together there a little bit more cleanly. So let's do the y's even faster right here. This should be r sine theta for all of them. So 3/2 sine of pi sixths. Sine of pi 6 is a half, so I'm going to get 3/4. 3/2 times sine of 5 pi 6. Sine of 5 pi 6, also 1/2, so I'm going to get 3/4 again. I wanted to draw the 3/2 again, but it's a radius of 0, so we're going to get 0 again. Notice for this. Oh my gosh, how many times am I going to write the 3? I'm trying to do this fast, taking more time now because I'm trying to go fast. 0 times the sine of 3 pi halves is 0 times -1, which is 0 again. So what are the 3 points that we arrived at? Our x values are 3√3/4, comma, 3/4. Then we got -3√3/4, comma, 3/4. And then we got 0, 0. So what I want to do now is let's go plot these 3 points in Desmos, and then we'll add the equation to the graph, and we'll feel all the deep satisfaction that we should feel right here. So let's pop over to Desmos. And what I want to do over here is I'm going to add a table into Desmos so I can graph a series of points. So up here in Desmos, you can add a table. And in this table, I'm going to throw in those 3 points that we just found. So I found 3√3/4. So 3√3 square root 3 over 4, and 3/4 was its partner. Then we found -3√3/4, and 3/4 was its partner. And then we found 0, 0 as the third point of interest right there. I'm at a ridiculous viewing window. So there's the 3 points where we're claiming we're going to see a vertical tangent line. The equation that we were graphing was r equals 1 plus sine of theta. And oh yeah, I think we nailed it right here. These absolutely look like the 3 locations on this graph where we would be getting a vertical tangent line right here. I think it's pretty obvious on the outside that these get these 2 vertical tangent lines right here. This one seems a little bit less obvious right here, because when I think about this sort of like peach shape right here, or sort of like the little butt at the bottom of the cardioid down here, I don't picture this being like a very sharp crack in the butt right here. But I mean, we could zoom in forever, because thank you, Desmos. And you know what? I can clearly see that this purple curve is getting to be infinitely steep at the origin right here, which is kind of hard to tell from a distance. This doesn't seem to be like needle sharp when we look at this from far, far away right here. That's just due to the thickness of the line as we zoom out right there, right? So I can see by zooming in, it's pretty clear that those angles do get to, or those slopes do get to be infinitely steep as we enter into the origin right there. So it looks like by doing our little derivative right there, we were able to appropriately identify the 3 locations at which we were finding those vertical tangent lines by finding where is the derivative undefined, meaning where are we dividing by 0 in that derivative equation right there. So I like this problem because it just kind of relates together a bunch of sort of like simple algebra ideas. We can solve quadratics, we can do trig manipulations, we know that functions are undefined when we divide by 0. We get our multiple solutions out of our trig equations, we can convert between, we can use theta and an equation to get r, we can use theta and r to get x and y. And so lots of nice relationships that we see in this problem right here. So there's our derivatives right there. We did one application of a derivative, finding tangent lines, in particular identifying that lots of polar curves have vertical tangent lines. And so in this case, we hunted for those, which is kind of special to polar curves that they have those out there. Let's go ahead and look at some other things, such as our area that's associated with polar curves here. So area associated with polar curves. So what we want to do is let's consider a general curve in polar space and the area that is sort of contained by, I don't know if beneath it is necessarily my best phrasing right there, but what I want to sort of picture for myself is what happens if we have some like curve out there in polar space, right? So there's some, this is some r equals f of theta. Well, what seems to me is that I no longer want to build Riemann rectangles since I'm not measuring in a rectangular coordinate system. I'm now measuring in a coordinate system where we have radii sweeping out angles. So what I'm now picturing instead is that it might be more appropriate for us to be subdividing rather than into Riemann rectangles, subdividing into Riemann sectors. So these are all going to be sort of like a subdivision of a circle, right? Or maybe I actually have to picture this one going like this and having a sector component like that. I think is slightly more appropriate. Oh dang it, we're remembering that these are just approximations, right? And as our number of subdivisions gets larger and larger, the size of each subdivision is getting smaller and smaller and smaller, and therefore the amount of error that we're accruing on any one subdivision is getting smaller and smaller and smaller. So I might picture this being sort of like my Riemann diagram. Um, and so again, our Riemann objects are circle sectors. Right, we're sweeping out a smidge of delta theta. Delta theta is the change in theta over which we have accumulated our next chunk of area out there with some r, where we can always find what the r is by just plugging in theta. That's just like saying before our change was a delta x, and we can find out what our new height is by just plugging in that appropriate x into our equation to solve for y. It's exactly the same idea. We're just accumulating our area radially rather than rectangularly. So it seems like our Riemann objects are circle sectors. So what we need to know is if we're going to accumulate an infinite number of Riemann objects, we need to know what the area of one general Riemann object is going to be, right? So I always like to picture for myself. So by the way, this is one of those things where I generally sort of like actually I kind of hate using this formula. When I teach trig, I encourage people to not actually use this formula, but it's finally going to be useful in calculus land here is how do we get the area of one sector, right? So if this was the area that I'm interested in, one sector is just like one chunk of a circle swept out by some amount of angle. So here's kind of what I'm thinking to myself. What my area of this sector should be is it should just be the area should just be pi r squared. This is the entire circle. All I want to do is multiply by the proportion of the circle that I am interested in keeping. So I'm going to say times the proportion of the circle. This is how I encourage my trig students to actually remember this formula is just do pi r squared, then multiply by the proportion of the circle that we are interested in keeping. In this diagram right here, we can see we are interested in keeping 1/4 of the circle. But how's a better way to describe that? Well, the better way for me to describe this is to say in this diagram right here, we are interested in keeping 90 out of 360 degrees. Out of the total 360 degrees in a circle, we are interested in the area associated with just 90 of them. Well, 90 over 360 is going to give us that 1/4. That should be our appropriate multiplication factor to find 1/4 of the area of a circle. And so what we're really going to get here then is that our area should be pi r squared. Now, how do I write mathematically the proportion of the circle? Well, I'm going to do this in radians, and I'm going to say out of the 2 pi radians in the entire circle, we are only interested in keeping theta of those radians. So theta is, in this diagram here, theta would be pi halves. So out of the full 2 pi radians, we're interested in keeping the area associated with pi halves of them. Well, pi halves over 2 pi is 1/4, just like it should be 1/4 of the area. Now, the reason why this formula is always done in polar and never done in degrees is because there's already a pi in the equation, so we'd like to bring in more pi's right here, and we notice pi and pi cancel. And this is actually going to leave us with area equals 1/2 r squared theta, which honestly is a little bit, in fact, sorry, well, whatever, it doesn't matter, it doesn't matter. So this is really weird to me because, and the reason I also don't like this formula is because how are we going to get an area for a formula of a circle that doesn't have pi in it? And that's because when we measure our angles in radians, those also have pi, so there's some pi cancellation. But this is a weird one for me to memorize because it doesn't seem like it's got the structure I think of. So again, when I teach trig, I strongly encourage my students to just do pi r squared and then multiply by a fraction. Technically speaking, that formula will always simplify down to this. But like when I teach trig, I think I like literally never even say this formula, even though it's in the book, because I don't think it's, if you're using this formula, it's more like you're just memorizing something, whereas this like requires like mathematical intuition of just multiplying by the appropriate fraction. I feel like this convinces me that people know math more than this does. However, we're not interested in conceptually doing math. We're interested in building a Riemann sum right now. So we need this cleaner version of our area of a sector right there. So this is by far the more practical one now that we're in integration land. So here's the deal. If we want to perform integration to accumulate the area associated with infinitely many, infinitely narrow, and when I say narrow, I don't mean narrow like a rectangle, delta x getting small. I mean narrow as in an angle, delta theta is getting small out there. Then we can perform the sum, right? So what I'm thinking is let's set up a summation right here. Well, all we're trying to do is add up a bunch of sectors, right? That should be the sum of just the 1/2 r squared delta theta. And now we take the limit as the number of subdivisions goes to infinity, or the limit as delta theta goes to 0. Either one of those are the equivalent limit statements. Then this should land us at the integral from theta equals a to theta equals b of 1/2 r squared d theta right there. So it looks like this is our good area formula right here, is that we're just integrating 1/2 times r squared with respect to theta, and we'll be given the theta bounds over which we're interested in identifying that region's area. So let's go ahead and see if we can take advantage of this formula here with a little bit of an example. And again, notice all we did is said, well, instead of using rectangles for rectangular coordinates, we should use circles for polar coordinates. And otherwise, we're just building our integrals in the exact same, conceptually the same way right there. Instead of summing up rectangle areas, we summed up sector areas. Instead of using the general formula for a rectangle, we used the general formula for a sector area right there. There was a delta term for the small change that we're going to experience. It turned into the D term over here. Like all this stuff, I hope that you're looking at this being like, that makes a bunch of sense right there, because it kind of really does. So here's our general formula right there. So let's go ahead and look at an example. So what I would like us to do is to find the area of one loop of the curve r equals 3 times the sine of 6 theta. Now, immediately the issue with this is I described the region of interest not like with an interval. I didn't say, oh, for theta from pi 6 to 9 pi sevenths do this thing. Like I didn't give you the actual bounds right here. So it seems like what we need to do is we need to go look at a picture in Desmos to determine the bounds. I need to consult Desmos to find bounds. So let's go take a look at this guy in Desmos. 3 times the sine of 6 theta. R equals 3 sine 6 theta. And what we're getting here is this really nice multi-petaled flower. And what I'm seeing here is we're interested in identifying the area of one petal, one loop of this flower that we're getting right here. And by the way, I might say to myself, so I guess the thing that I'm seeing here is this. I'm seeing that in the first quadrant, there are 3 loops, and this thing seems to have a ton of symmetry. So I'm thinking that 1/3 of 90 degrees should get us one of our loops. The thing I want to caution you about right here is that you need to check out these types of bounds in Desmos yourself. The thing that totally could have happened right here, the thing that does happen occasionally with our stuff here, is that it could be the case that you would have actually gotten 2 loops if you did 0 to 30. Polar things are kind of tricky that when they parametrically sweep out the curves, they don't necessarily just like do like loop, 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 like in an order around. Sometimes they do one loop on one side and then it's opposite partner. Then the next loop up here, then it's opposite partner down here. Other times, when you do 0 to 2 pi, maybe that actually swept out the entire flower shape twice and you didn't realize that, so that it was actually maybe giving us double the area, stuff like that. And so it's really meaningful for you to stop and say, okay, my guess is that my bound should be from 0 to 30. Let's change this to like 28 and see, okay, I'm really convinced that 0 to 30 is correct right here, that we're not like doubling over ourselves, that it seems like if 28 degrees got us just barely shy of completing the loop right there, and then we go to 30 and we're there, and we go to 32 or 33 and we're a little bit beyond it. I'm highly confident now that 30 degrees, 0 degrees to 30 degrees is going to be good for one loop. So I'm just saying, polar things will screw with you a little bit. So you need to double check, or double check, not just check in Desmos to see what your graph looks like. Double check. Play around with your bounds over which it's graphing it. Make sure that you're not being trickily misled by overlapping parts or loops not being created in the same order that you thought they were, or whatever. And also recognize that you can convert between radians and degrees down here. So whether you want to think about this in either format, clearly we're in degrees right now. I could click radians, and it's obviously going to give me the whole thing because 30 radians is going to be more like 8 pi. So it's probably swept out this whole thing about 4 times right now. And so clearly here I could also just go to pi sixths, and we're getting that same one loop. So I think theta being, now, by the way, I should actually say, you are welcome to investigate this in degrees or radians, but recognize that this formula that we just made here, that the formula that we just made here is absolutely dependent on being in radians here. Theta must be in radians. So I'm going to write that here in my, it'll kind of highlight this note right here. Theta must be in radians. A and B must be in radians. All right, so this says do all your math in radians. If you like to think in degrees, there's nothing wrong with that. Convert to radians to do your math. So basically what I think I've found here is I've found from Desmos that we should be getting theta should be going from 0 to pi sixths will get us one loop of this thing. So let's go ahead and build our area integral here. So area should be the integral from 0 to pi sixths of 1/2 r squared d theta. Well, we've got an equation for r right there, so I think we're going to be in good shape to make this happen. 0 to pi sixths. I think I'll pull my 1/2 out front. I think it's going to get some buddies though in a second here. R squared should be 9 sine squared 6 theta, d theta. I certainly want to pull that 9 out front here as well. 9/2 integral from 0 to pi 6. Now we should say to ourselves, all right, what the heck are we going to do with our sine squared of 6 theta right here? I know that having that trig function being squared is a little bit problematic for me. I feel like this is a good case for us to pause and consult our trig stuff right here. So let's go ahead and take a look at what we can see out here to help ourselves out with our sine squared of theta right here. So I'm looking to replace sine squared, which I can't integrate, with something that I can integrate. And so if I come over here to my table, let's zoom in a little bit right here. I'm looking for sine squared, and I'm looking to replace it with something that I can actually integrate. And what I'm seeing here is a bunch of stuff that doesn't have sine squared in it, right? I'm looking at this like whole left side over here. I see I could do sine squared equals 1 minus cosine squared, but then I'm just stuck not being able to integrate cosine squared, although I know cosine squared crops up in a double angle formula, so I could do that if I needed to. Nothing useful here. Nothing useful here. Nothing useful here. I see a sine squared here. And this actually looks useful because the remaining components other than sine squared are things that I can handle. A constant and just a cosine of a double angle right there. So I think that this guy seems to be a useful substitution for me to make right there. So let's go ahead and copy down that identity and let's take advantage of this guy here. So I'm seeing cosine of 2 theta equals 1 minus 2 sine squared of theta. So I'm seeing cosine, and I'm going to write it like this. Cosine of 2x equals 1 minus 2 sine squared of x. I have sine squared of 6 theta right here. It seems like we're going to end, so 6 theta is like x. It seems like we're going to end up with a cosine of 12 theta then, therefore, because this is double whatever that angle is going to be right there. Let's go ahead and solve here. This should be cosine of 2x minus 1 equals negative 2 sine squared x. And I'm going to divide everything by negative 2, so I'm going to get a 1/2 1 minus cosine 2x equals sine squared of x. So we've got sine squared of 6 theta. So 6 theta is equal to x. 2 times 6 theta will be 12 theta, and this is our new replaced quantity right here. So it looks like I'm going to be able to take this guy with this guy right here. And this is going to allow me to rewrite our area as 9/2 integral from 0 to pi sixths of 1/2 times 1 minus cosine of 12 theta. And it's 12 because we have doubled our angle. That was officially a double angle formula that we just used right there. So some things I can see. One, I'm clearly going to factor this 1/2 out front, so we're going to get a 9/4. And now I think we can go ahead and integrate. 1 minus cosine of 12 theta, d theta. All right, so doing my integration now, this is going to give me 9/4 times, it's going to give me integral of 1, d theta, is just theta. The integral of cosine should just be sine, so I'm still going to get the minus sine, but I think I need a 1/12 to pop out here to cancel out the 12 that would pop out if I now took a derivative. And we're evaluating this guy from theta equals 0 to theta equals pi sixths. To do this, now I'm going to get a 9/4 times, I'll open a big parenthesis here. My first grouping here should be pi sixths minus 1/12 of sine. Now, pi sixths times 12, that's just 2 pi. That's actually a really convenient value for me. And even further, the sine of 2 pi is a really convenient value for me. Minus, plugging in 0, I'm going to get 0 minus 1/12, the sine of 0. Well, sine of 0 is the same as sine of 2 pi, that really easy value for me. So you should notice real quickly that this is 0, 0, and 0 for those three values right there. It looks like the only term that survived the evaluation of my integral was the pi sixth. So I'm getting 9/4 times pi sixth, and therefore I'm getting 9 pi 24ths is the area of one loop. Cool. Not too bad here, really. I mean, this is the bulk of this problem was just the trig stuff that you've done before. We needed to, I think going to Desmos to consult Desmos to help us find our bounds is a really meaningful thing to be able to do, but really not too bad. Again, just remember that like we didn't get tricked right there. Polar curves can trick you, so make sure you play around with those boundaries a little bit to make absolutely sure that you're identifying the correct bounds of integration right there. It's easy to accidentally get double what you thought, or I don't know. Just some weird things can happen with polar curves out there. They're harder to just judge at a glance, so be careful with that. And otherwise, in this one, the trig wasn't too bad right here. We got a sine square. I'm positive that we've essentially done this integral before. I got to say, this is probably our most used identity all semester here is the cosine of 2 theta stuff right here. So nothing too crazy here, I don't think. So I really like this right here, that we've sort of swept out an area in polar form rather than sweeping out an area with rectangles in rectangular form. So as our last topic for the day, let's go ahead and hit up some arc length. The arc length formulation here, I really like this kind of building this formula right here is really cool, because this is one of those in the long list of cases where gross trig stuff often turns into nice trig stuff. I think that's the theme of what we're going to look at right here. So let's go ahead and check this guy out. So when we first did arc length, we came up with this formula for arc length that looked like the integral from a to b of the square root of 1 plus dy dx. Sorry, I actually want to, well, okay. So in the case that we had our y equals f of x stuff, right? This was before we got even parametric stuff. We got this formula here. Or alternatively, if we wanted a dy integral, we would just flip this derivative right there, right? Then we came along and we said, all right, well, if we instead had that x was going to be a function of time and y was going to be a function of time, or I shouldn't necessarily say time, but if f and y, or if x and y are parametrically defined, then we said that our arc length formula was going to be this alpha to beta of the square root of, and we did dx dt squared plus dy dt squared with respect to dt. So therefore, what you should be thinking here is this is basically exactly what we're doing. We're just parameterizing now in terms of theta instead of in terms of t. So this should be dx d theta and dy d theta. Like that, I mean, we're basically just copying this stuff over here, right? So r is a function of theta, and x is r cos theta, and y equals r sine theta. So now I'm going to just draw an arrow right here and say, listen, we're basically just rewriting this one. Our arc length should just be this integral square root of dx d theta squared plus dy d theta squared d theta. But what is not clear to me is what's dx d theta and what's dy d theta. And even more, if we square them and add them, what are we going to get right here? So let's simplify the radical term. And I'm recalling here that dx d theta, we've already done this, dx d theta is dr d theta times cosine of theta plus r, oh, excuse me, that's minus, because we're going to get the derivative of cosine here in a second, minus r sine theta. And our dy d theta, that's dr, just doing the product rule here, dr d theta, derivative of r, leaving the sine term left alone, minus r gets left alone times the derivative of sine is cosine of theta. So I know what dx d theta and dy d theta look like. I want to square them and add them. Now square, sum, and simplify. So what are we going to get here? Well, I'm just squaring these two terms and adding them together and hoping to see some simplification. So I'm seeing dr d theta cos theta minus r sine theta squared plus dr d theta sine theta minus r cos theta squared. And I'm hoping that this is going to look less gross than this. Remember, this is the term that's going to be sitting underneath the square root for your integral right here. As it stands right now, I'm looking at this being like I'll never be able to integrate this. So hopefully things will become nicer. And what you should see is we're clearly squaring a bunch of trig terms. So I'm hoping for lots of sine squared and cosine squared coming together here. So I'm going to get a dr d theta squared cosine squared of theta minus 2r dr d theta sine theta cos theta. I know that when I'm expanding a binomial, I get 2 times the first term times the second term. This is all those terms multiplied together times 2. And then I'm going to get the square of the last term, which will be plus r squared sine squared of theta. So that's my whole first one. Plus, very similarly, I'll get a dr d theta squared sine squared. That's the first term squared. I'm going to get 2 times the product of the two term. Oh, wait a minute. Didn't I have a... Okay, I did write this down. I'm glad I stopped to peek at this right here. Okay, all right. Let me show you my tiny mistake I made. I'm glad I caught this here. The derivative of y with respect to theta should have had a plus right here because this said take the derivative of r and leave sine alone, plus leave r alone and take the derivative of sine. Derivative of sine is positive cosine, so we do get a plus sign right there. That plus sign is going to be the plus sign that's right there. And therefore, we do have all positive terms here. Okay, I'm glad I caught that one right here. So now I'm going to get a plus 2 times the product of all. So 2 well, just to keep my ordering the same as I wrote the other term that looks like this, 2r dr d theta sine theta cos theta, and then plus r squared cos squared theta. All right, so there's my second grouping of 3 terms. Now the thing that you should notice right away is one thing. Boom, this term and this term clearly cancel away together. We've got a positive and a negative of the same thing. The second thing that I'm seeing here is I'm seeing that this term here, dr d theta squared cosine squared, also has another dr d theta squared sine squared. So when we add these together, my question to you is how much dr d theta squared do we have? Well, we have cosine squared plus sine squared of it. And cosine squared plus sine squared is just 1. So it seems to me like the first term that I'm going to end up with over here is just a dr d theta squared. Now, what's my last term going to look like over here? Well, the last components that I have over here are the r squared sine squared and the r squared cosine squared. And so once again, I say to you, how much r squared do we have? Well, I have sine squared plus cosine squared of it, which means I have 1 of it. So that's literally just a plus r squared. And so that says to me So remember, all this math that we just did, this was for the area, this was for the term that's underneath the square root in our arc length formula. So it now seems like we've found, so we have that the arc length formula in polar is the integral from a to b of the square root of dr d theta squared plus r squared d theta, right? So this is the derivation of the formula here, is that we literally just took our parametric formula and we said, well, yeah, x and y are parameterized by theta, not by t. And so we stuck theta in there. We knew what the equations were that parameterized it. X equals r cos theta, y equals r sine theta. And so we just evaluated and simplified. And unsurprisingly, when you square and add together a whole mess of trig terms, a bunch of stuff falls out because sine squared plus cosine squared equals 1, right? And that's all that happened twice. We had one cancellation and two sets of sine squared plus cosine squared equals 1. That's about as nice as that could have possibly simplified for us right there, right? So as our final example right here, I'm even just going to have to have us set up an integral. Find an expression for the arc length of one loop. Notice it does not say find the arc length of one loop. It says find an expression for the arc length of one loop. We're going to see if this is going to lead us to an integral that's perhaps slightly beyond our capabilities. I think that I could technically do it, but I'm not interested in spending 20 minutes doing a trig integral right now. So let's state the integral, let's simplify that integral, and then let's go ahead and ask technology to help us evaluate the value of that integral right here. So we should be finding that L is going to be equal to the, and so remember, we're looking at one loop, same previous thing right here, so we're still doing the 0 to the pi sixths. The square root of, now, the derivative of r with respect to theta, I'm seeing here should be the derivative of the outside function, sine is going to go to cosine. Derivative of the inside function is going to pop us out a factor of 6. So this is going to be 18 cosine theta squared. That's my dr d theta squared. Plus, I just want r squared, 3 sine of 6 theta. Oh, and I'm realizing I typoed the last one, because the last one, I didn't drop my 6 in there with the theta. So I gotta be a smidge more careful. Cosine 6 theta squared. Okay. So this, I mean, this is my expression. I'm essentially done. I'm gonna clean it up a little bit for myself just to be a respectable mathematician here. But that should be just our expression here. Pi sixth of the square root of, let's see, 18 squared is 324 cosine squared of 6 theta plus 9 sine squared of 6 theta d theta. And there we go. I've come up with an expression that is representative of the arc length of one loop. So let's go ahead and estimate what we're going to get, and then let's throw it into Desmos, and then we'll say, oh, cool, we nailed it. So what I want to do is I want to make an estimate in Desmos. I want to guess. So my question to you is, about what would you guess the length of this one loop should be right here? And here's kind of what I'm thinking. So stop for a minute, pause me if you need to, make a guess. How long is this loop? Guess it. Okay, now that you're on pause, what I'm seeing is this. It seems to me like this loop is kind of basically going almost like 3 units out and 3 units back. But because it's got that loopiness to it, I'm thinking it's going to be a smidge longer than that, right? But I'm seeing 3 out and 3 back would make 6. So I'm thinking a number slightly bigger than 6, I think would be believable to me here. I'm also thinking, like, if we were to like take this loop and like lay it down so it was perfectly on the axis right there, I think it would almost be making it to 3 or even a bit past 3, and then it's looping so it's not just a straight line from 0 to 3. So again, I'm thinking a number slightly bigger than 6. And so what I'm going to do is I'm just going to go ahead. And so again, my guess is a little bigger than 6. So let's go ahead and just see if Desmos can just straight up do this for us here. I'm going to do my integral from 0 to pi sixths of, and what do we got? We got the square root of 324 cosine squared of 6, and I'll just call it x because it doesn't matter, plus 9 sine squared of 6x dx. And what do you know? Desmos is telling me that this is a little bit longer than 6. So I very much agree. And again, making these guesses matters because if you don't make guesses, then when you have new formulas and you're using them, you're like, I don't know if this is right. Stop and make a visual estimate for yourself. I feel very confident that the math that we've done is correct right now because this guess completely agrees with what I felt like I should have been getting out. And whether or not I can do this integral by hand or not, is to be determined. For your gold star for the week, if you want, figure out how to actually integrate this thing. I, I think we can maybe do it. I'm not even positive. I tried for like a few minutes yesterday, and then one of the babies woke up, and I was like, "Oh, done with this integral." Maybe I don't. I don't know. I'm torn. Anyway, the point is, I can use technology to help myself evaluate it. It completely agreed with the estimate that I made for myself right here. So 6.225. Let's go ahead and throw that in here. Um, so there we go. We found our expression for it. This was sort of technically what I asked, is find an expression that represents the arc length, and then we estimated it using technology to get 6.225. I don't know how to get an exact answer for that one right there, but that's okay. So there we go. So again, I hope, like I said at the beginning of this class, I hope that you guys agree that this is, in a sense, a very, very similar section to what we just did with all of our arc length stuff right there. Not really huge new ideas right here. You guys are easily able to see where our formulas are coming from for derivatives, for integrals, for arc length formulas. All these things, I think it's very natural for us to derive those formulas on our own. Like, I don't think those are some like big monumental ideas. We were just slotting things into the correct slots and evaluating and simplifying because trig stuff often simplifies nice. So I hope that you find these sections to be interesting and not too terribly difficult. Again, some of these formulas probably going to lead us to crazy hard integrals, but like what doesn't? Like everything does that these days. So I don't consider that to be the hard part. The conceptual part of building these formulas, that's what I think is the most important thing. And I think they're all relatively followable this week. So I hope that you're down with all three of the derivations that we did today, defining derivatives, areas, and arc lengths in polar form. I think all three of those are very accessible. So I hope that you guys stuck it out with those guys today and understand where those came from. That's all that we're going to talk about here for polar in this class. Remember, when you guys take 50C, Calculus 3 next semester, you're going to spend a pretty decent chunk of time. It'll be like 2, 3, 4 weeks where you'll be constantly kind of rotating through different formats of uh, systems of measurement like rectangular, polar, and you're also going to get cylindrical as a third one out there. It's sort of like halfway between the two right there. Um, and so you'll see a bunch more of that kind of stuff in 50C. So today, then, therefore, this minute of the video right now represents sort of the last meaningful integration that we're actually going to do for most of the semester here. Chapter 11 is going to take what will feel like a pretty sharp left turn on us right here to talk about a big chunk of things that aren't explicitly about doing what you currently think that calculus is, but these are ideas that are absolutely central to like the core meaning of what calculus is all about, which is really saying, how can we make infinity make sense? And the deal is that we've talked about lots of ways that we can make sense of infinity. We've talked about what happens as two numbers get infinitely close together. That helps out with derivatives. We can talk about what happens when a number gets infinitely large or infinitely small. That's with limits, or infinitely close to another number. That's limits. We've talked about what happens when we try to add up an infinite number of infinitely small objects to get an object that's one dimensional larger than the previous object. But there's still lots of other infinity questions out there that are perfectly reasonable to ask, just like all those were, but just that we haven't explored yet. And so chapter 11 is going to show you that there's a whole nother side to this calculus discussion that doesn't necessarily directly deal with derivatives and integrals. But since infinity is involved, derivatives and integrals are going to get involved. And so chapter 11, I don't know. Prepare yourself. So I'm also going to be making 2 videos just for section 11.1 because it's got kind of a bunch of introductory things that aren't too difficult, but the book does expect everybody to understand a certain proof technique that I also expect you to understand, but I don't necessarily think that you guys have all seen it. So I'm also going to be making, the reason there's 2 videos is one is to cover the bulk of 11.1. The other video is to cover the proof technique that's going to get used a lot in chapter 11 that you guys need to get comfortable with. So that's why there's two videos for 11.1 coming up here. So this wraps up our regular calculus component of this class, and we're going to see sequences and series in chapter 11 for the remainder of this course here. I will see you guys in the 11.1 video. Have a good one.